So now we're going to start, now we know what derivatives are and how to find them. We're going to start talking about some applications of derivatives. The first application we're going to talk about is something called related rates. And related rates is where you happen to know that one quantity is related to one concept and you want to try to relate to another one. So like an example is, you know how fast a, let's say you have an oil leak from a ship out in sea. It's going to come out. Usually the oil leak is going to leak in kind of a circular shape. And we know how fast it's leaking from the ship. So we know the rate at which it's leaving the ship. And what we want to know is, we could then find out how big that's the radius is changing over time. But we might want to know how fast is the area changing over time. So we want to find that rate of how fast the area is changing over time that's related to how fast the radius is, because area and radius are very related to each other. So the way we do this, and I'm going to actually use that as my example, is I want to find out the change in area over time. I know the change in radius over time. That's known to me. But I want to find this. Well, I know how area and radius are related. If we have a circle, we know that area is pi r squared because we have a circular shape. So when I look at that, I can find that the change in area over time, using the idea that area depends on radius, we can take the derivative of both sides of this with respect to time. And therefore, we would have kind of think of it as implicit differentiation. You take the derivative of area with respect to radius, then you'd multiply that by the derivative of radius over time. So this really is an implicit differentiation problem. You can find this area just fine because you know this is 2 pi r, so you can get the outside function, and then you're going to multiply that by the derivative of the inside function, which is the dr dt. And then you can find out how they're related to each other. So this is a lot of what we see that we're going to look at for related rates. So let's go ahead and try an example. This is example 14 from the Stewart Concepts and Context textbooks, version edition 4. And this says a street light is mounted at the top of a 14-foot tall pole. A man 6 foot tall walks away from the pole with a speed of 5 feet per second along a straight line. How fast is the tip of his shadow moving when he is 40 feet from the pole? So that's a lot of words. And so it would be very helpful to draw a picture. I think pictures are very useful here. So first off, I have a pole. So here's my light source. And then I have a person, a man over here. And he's walking along the street. I'm assuming, and this is an assumption, I'm assuming we have a level street. They didn't say that. We're going to have that assumption. We know the height of this pole is 14 feet. And we know the height of the person, that person's 6 feet. And we know the light is going to cast light onto him, and he will cast a shadow. And what we want to know is how fast is his shadow moving when he is 40 feet from the pole. So we know how far away he is, but he keeps changing. So that actually does change. So that's not a constant value. So we have to think about that as not being constant. And then we have to figure out what to do with the rest of this. Okay, so the first thing I'm going to look at is the fact that this is actually changing. So since he's walking away, this distance here from here to here is changing. So we can talk about what that distance is. That distance, let's give it a name. We'll call it, I don't know, x. So x is the distance from the pole. And it's changing. So I can't call it a number because it's changing. I also can talk about the length of the shadow. And again, that's changing too, because as he's moving farther from the light source, the length will change. So let's call that L. So that's the length of his shadow. Okay, so we have all that information. We know how fast the distance from the pole is changing over time because that's his speed. So we know dx dt, that's his speed, which is 5 feet per second. So we know that information. We want to find how fast his shadow is changing. So we want dl dt. That's what we're looking to find. Okay. So that's what we want to find when he's 40 feet away. So we're not caring about anything else. So we could say that his distance, x, is 40 feet. All right, so this is what we want to have. So let's see if we can figure out how to deal with this. So first off, one of the things I notice is I have a right triangle, but I don't know the hypotenuse length. So that doesn't help me to know I have a right triangle because I have no idea what this length is. So that's not going to get me much help. But I also notice I have two right triangles. I have this right triangle, which is what the man makes with his shadow. And I have this right triangle, which is the from the light source. So I have two right triangles, so I can use similar triangles. I happen to know that this distance along the long line, which would be x plus L, over top of this height, which was 14 feet. Let me make sure I got that right. Yep, 14 feet. So I have this long side over this side here. That's going to equal, with similar triangles, that's going to equal this long side, which is L, over its height, which is 6. And so I have this nice little relationship here. So let's go ahead and do it, just a little bit of work with this. Maybe I'll multiply 6x plus 6L equals 14L. And then 6x is going to equal 8L. So x is going to equal 86L. So I now have a relationship between x and L. Okay. Well, that's great. This may not be the best way I want to do it, so I might want to actually say that L is equal to 6/8 x, which of course, let's reduce that a little bit because I'm having a hard time saying that. And that would be not 2, but 3/4. Because 2 is common to both. So it'd be 3/4 x. So that might be a little bit easier. It depends on which one we want to go with, which way we want to do it. So we've got 4/3 L here, and then we've got L is equal to 3/4 x. Okay, let's move this over just a little bit. I think we got a little too much. Looks a little crowded here. All right, so we have those two values, and now let's see what we can do with it. So the next thing to realize is, again, I want dl dt. But I don't know how L is related to T. That's what I want to find. But I do know how L is related to X. I do know dl dx. dl dx is something I could find. I could actually find this derivative without any problems. But I wanted L dt. So what if I multiplied this by dx dt? That would get rid of the x's, and I'd have dl dt. Which I know dx dt, that we were given. We know how fast he's walking. So let's see if we can keep going with this. dl dt would be the derivative of L with, dl dx would be the derivative of L with respect to x. So that's 3/4. dx dt, going back up to our problem, dx dt was equal to 5 feet per second. All right, so we have 5 feet per second. So we end up with 15/4 feet. Now, dl and dx are both in feet, so those would cancel, and so we're still going to have feet per second. All right, And so that's how fast his shadow, tip of his shadow, is moving. All right, let's try one more of these. Another example is the water is leaking out of an inverted conical tank at a rate of 10,000 centimeters cubed per minute at the same time that water is being pumped into the tank at a constant rate. The tank has a height of 6 meters. The diameter at the top is 4 meters. If water level is rising at a rate of 20 centimeters per minute, when the height of the water is 2 meters, find the rate at which the water is being pumped into the tank. All right, again, lots and lots of words. So it might be useful to draw pictures. So we have a conical tank. That just means a cone. So there's my cone. I want to find out when the water is rising and it's rising at a certain rate, and I want to find out how fast is the water rising. I want to find actually how fast the water is being pumped into the tank. All right, so I still want to find a rate, but the water is rising. So since the water is rising, it's changing. So think of this as being the level of the water. So this is where I am. It's going to have some radius because it's a conical tank. So no matter what, it's going to be spreading out and it's going to have a certain radius. And it's going to have a certain height that it is from the base. Okay. So one of the things we remember is we do know the height of the conical tank. The height of the conical tank, if you remember, was 6 meters, and the diameter at the top is 4 meters. So we know this is 6 meters, and we know the whole length here is 4 meters. So the radius would be 2 meters. So we know that. We have that information. We can work with it. All right, so we know how fast the water is going in. We don't know how fast the water is going in. We know how fast the water is coming out. We know how fast the rate the water is changing, the height is changing over time. So we have all that information. So let's see if we can figure out some things in. So first off, we have a volume. So let's call V volume. And we have some rate in, which we don't know. So let's give it a name. Since we don't know it, let's give it some name. I'll call it R for rate in. All right. So the water is also coming out. So we do have that problem, the change in the volume over time is going to equal the rate in, which we call R, sorry, I called it R, not C, minus that rate out. And the rate out was equal to 10,000 cubic centimeters per minute. So that's a constant. We know what that is. It's not going to change. So that's not changing. So we can subtract it off. And again, that's cubic centimeters per minute. What we want to know is how fast is the water being pumped in. So we have this rate in. We want to find out what that is. And that's what we're looking to find. Again, we have a few of the variables here. We have R, which is the radius. And we have H, which is the height. And we know how fast the height is changing. The height is changing. Again, back up here, the height is changing at a rate of 20 centimeters per minute. So we know that when the height is forgot to look at that. When the height is 2 meters. So when the height is 2 meters, we know that this is changing at 20 centimeters per minute. So it might be useful to kind of look at how does volume, because we know volume changing over time. We know dH dt, but we don't know what R is. So it might be helpful to know what is the volume formula related to height. So the volume of a cone is 1/3 pi r squared times h. And the reason that is the radius of the area of the base is pi r squared. The height is h. And the 1/3 is because this would be, without the 1/3, it's the volume of a cylinder. When we take into a cone, it becomes 1/3 of that. So we have this information. But the problem is we have the radius and the height both in here. We don't like having two variables going on in here. So maybe we should find some way of relating height and radius together. So remember that what we have is we have a height over the radius of my cone. And we happen to know the height and the radius here. They actually form a similar triangle. So we're using similar triangles again. They form a similar triangle with the similar triangle of 2 meters to 6 meters. So h over r is going to equal the 6 over 2. And we want to keep h because I'm noticing that we have dH dt. So we want to get rid of the r. We want to get r in terms of h. So first thing I'm going to notice is that we have h is equal to 3r. Therefore, r is equal to h over 3. So we now have that. So I now have the volume is 1/3 pi h over 3 squared times h. So we now have that information. And so we now can write this, well, 3 squared is 9 times 1/3, that's 1/27th. Pi h squared times h is going to be h cubed. So we have this as our function for our volume. Now we can look at dV dt. We want to find dV dt. We happen to know that, again, we know how h is changing over time. We know how volume is related to h. So we can actually take dAV dH times dH dt. So we can find out how the volume is changing over time, which would then allow us to figure out what R is. Oops, obviously didn't write here very well, so I'll change that just a little bit. So dV dH, that would be, bring the 3 down, you've got 1/9 pi h squared times, remember dH dt, we actually know at a certain value. So we're going to leave it as dH dt right now because it only is at a certain height that that's happening. And so at a certain height, at the height of 2 meters, that dH dt was 20 centimeters. So we're going to go ahead and look at this as dV dt at 2 meters, at h equal to 2 meters. It's going to be 1. So one thing to mention is that h is in meters and everything else is in centimeters. So let's change that meters into centimeters. That will be 200 centimeters. All right, so now we've got h is equal to 200 centimeters. So that's 1/9 pi 200 centimeters squared times, and that was 20 centimeters per minute. All right, so all we gotta do is find out what all of this is equal to. 200 squared is 4,000 times 20 divided by 9. And that is, I'll have to take out a calculator because I don't know what all that is. So we have 200 squared times 20 divided by 9 times pi, of course. And so that's approximately 279,252. So I'm going to do that as approximately equal to, because I did the pi. So 279,252.7. And this was centimeters. So centimeters squared. This was centimeters, so it's going to be centimeters cubed. And this was per minute. And that's good because volume should be in centimeters cubed. Now that we have that, we can find out what R is. R is the VDT minus how much is being pumped in, which was 10,000. And so now we can find out approximately that'll be 279,252.7 minus the 10,000. And you now can find out how fast is the water being pumped in. And the water is being pumped in at 252.7 centimeters cubed per minute. And that's how we do related rates problems.